Right, welcome back to SMAR 3116. That is SMAR 3116. Right, and today I'm looking at series solution near an ordinary point. Right, so far we looked at DEs or differential equations where the coefficients were constant, but now we are going to look at slightly different problems where my P of X, P, Q, and R here themselves polynomials for now. Let's assume that these are polynomial functions of some arbitrary order, right? And that there are no common factors. That is, I cannot factor out any terms between P, Q, and R. So right. So if we wish to solve our equation star here in the neighborhood of some point, say x naught here, then the solution of x star in the interval that contains x naught is closely associated to the behavior of P in that interval. And the point x naught is said to be an ordinary point. It's an ordinary point if P at x naught is not equal to 0. Otherwise, we call it singular. Otherwise, x naught is singular if P at x naught equals to 0. Right. So, because x naught in this case is an ordinary point, that is to say, P at x naught is not equal to 0, we divide by what? By P of x to get y double prime plus, I'm going to use small lower cases now, y prime plus rx of y equal to 0. Here, of course, I'm assuming that q of x is nothing but what? Capital Q of x over P of x, and Rx is nothing but my capital Rx divided by P of x. Right, and we solve we are solving x star in the neighborhood of what? Of x naught. Right, so we assume, or we search for a solution y of x, which is given by a naught plus a1 x plus a2 x squared plus on and on, so that this in compact form can be written as the sum from n equal to 0 up to infinity of a n x to the n, sorry, of x, in fact this is x minus x naught to the power n, right? Sorry. This is y of x is equal to a naught plus a1 x minus x naught plus a2 x minus x naught, so that this is given by the sum from n equal to 0 up to infinity of a n x minus x naught to the power n, right? And we're assuming that the series converge in an interval that's determined, or that's given by x minus x naught less than some rho for some rho greater than 0, right? Maybe as a way of an example, solve the first order ODE, ordinary differential equation, given by y dash is equal to 2 x by y, using the series solution. method. Right, to start, we assume, of course, solution. We assume that our y of x is of this form here: a naught plus a1x plus a2x squared plus on and on. Nothing but n equal to 0 up to infinity. A n x to the n. Right, and my y prime of x. So I'm just differentiating y with respect to x. This is going to be given by what? By a1 plus 2 by a2x plus 3 by a3 x squared plus on and on, which I can rewrite in compact form if I want as the sum from n equal to 1 now up to infinity of what? Of n by a n x to the n minus 1. Right, but for now I'm going to ignore these expressions here and then plug. If I call this one what? I call this one 1 and call this one maybe 2. Plug 1 and 2 back to my DE. So what I'll have is what I'll end up getting is what? It's A1 plus 2A2 plus 3A3. Oh, this is x squared plus this next term would have been 4x to the 3 plus on and on, being equal to 2 by x by y. But y is what? A naught plus a1x plus a2x squared plus on and on up to the end. Right, and then I expand this and compare coefficients. Note that a1 plus 2 a2x plus 3a3x squared plus the other terms here will be equal to what? 2 a naught x plus 2 a1 x squared plus 2 a2x to the 3 on and on. And clearly a1 because I can compare the constants now. Constants a1 is equal to 0 because I can rewrite this as 0 plus that term. So a1 is that. Then comparing the terms in x, I end up with what? Terms in x, I end up with the 2 a2 is equal to what? 2a2 is equal to 2a naught x, just 2a naught. Right, then terms in x squared, 3a3 is equal to what? 2a1 but a1 is equal to 0. This implies that a3 is also equal to 0. Then terms in x to the 3, this would have been a 4 equal to 2a2, and this implies what? But a2, because here this implies that a2 is nothing but a naught. Therefore, a4 is going to be a4 is equal to half of a2, but a2 is nothing but a naught. And if we continue in this fashion, we note that a1 equals a3 equals a5 equals a7 equals to 0. In fact, all odd terms, right? And then the even terms, that is a2k, these are given by what? By a naught over k factorial. Because if I were to do if I were to do this, you'll note that this is given by a naught over k factorial, so that my series y of x, my y at x is nothing but what? A naught. I can factor this out, remains 1 plus x squared plus x to the 4 over 2 factorial if you want, plus x to the 6 over 3 factorial plus x to the 8 over 4 factorial, plus on and on. And using elementary functions, you note that this here, this thing here, is nothing but the Maclaurin series of what? Of e to the x squared. So that my general formula is given by y at x is equal to a naught e to the x squared, right, where a naught can be determined using some initial conditions or auxiliary information. So actually this is one way. Alternatively, we have y of x being equal to what? To the sum from n equal to 0 up to infinity of a n by x to the n, and y prime of x being equal to the sum from n equal to 1 up to infinity of n a n x to the n minus 1. Right, and plugging these into my original differential equation, I have this sum here from n equal to 0 up to infinity y dash n a n x to n minus 1 being equal to 1, 2 by x of yx. So this power here pops up by 1, and this becomes the sum from n equal to 0. This becomes the sum from n equal to 1, n equal to 0 of what? A n x to the n plus 1. Right, and I can shift the left hand side. I can shift the left hand side so that my generic term is in the form x to the n plus 1. Right, so I want to write this series as a series whose generic term is x to the n plus 1, because I've got an x to the n plus 1 this side. So going back, I can let m equal to n minus 2, which implies and is implied by that n is equal to m plus 2. And I can sum this from now what? can sum from m equal to 0. M equal to 0. On the left hand side, I'll have a1 plus the sum from m equal to 0 up to infinity of m plus 2 by am plus 2 by what? By x to the n. N is m plus 2 minus 1. So this term becomes now what? This would be equal to a1 plus the sum. Right, I can change my m back to n from n equal to 0 up to infinity of n plus 2 by an plus 2x to the n plus 1. And then this implies what? That I have a1 plus this sum here from n equal to 0 up to infinity of n plus 2 into an plus 2 by x to the n plus 1 to equal to the other side 2 n equal to 0 up to infinity of an x to the n plus 1. Right, note that there are no constant terms on the right hand side, so this implies that my a1, this term here, is nothing but equal to 0. And having done that, I can compare these two here, and since they are, I'm summing from n equal to 0 to infinity, and this side I'm also summing from n equal to 0 to infinity with the same generic term, I can simply compare the coefficients. So this implies that n plus 2 by an plus 2 is equal to 2 by an. And I have this now as what? An plus 2 over n plus 2, right? Starting from n equal to 0, 1, 2, all the way up to infinity. And note that when n is 0, I get a2 is equal to 2 by a naught divided by 2. I get a2 is equal to a naught. And when n is equal to 1, I get a3 equal to 2 a1 over 3. But this is equal to 0 since a1 is equal to 0. And then when n is equal to 2, I get what? a4, which is equal to 2 times a2 over 4. And this is equal, this implies a4 is equal to what? 1/2 a naught. Right, I think at this point I can ignore all odd terms, because when n is 3, I get what? a5, which depends on a3, and a3 is equal to 0 since a1 is 0. So I can ignore those and take a few cases when n is equal to 4. When n is equal to 4, I generate a6, which is given by 2 by a4 over 4 plus 2, 6. And this implies a6 is equal to a naught over 6. Note that this is by 2. This would give me 1 over 3 by a4. But a4 is half a naught. So I get that. So when n is equal to 6, I get a8, which is equal to 2 a6 over 6 plus 6 plus 2, this is over 8, so I get 1 over 4 times 1 over 6, so my A8 is nothing but 1 over 24, in fact A naught, right, A naught over 24. And if you note, I can rewrite these terms now as well. In factorial form, this is what A naught is just A naught divided by 0 factorial. This is 2 over 2 factorial, so this is still A naught over 2 factorial, and this I can write as A naught over 3 factorial, this I can write as A naught over 4 factorial. So that continuing with the pattern, you would note that all these terms will be given by what? By the generic term A by 2k is equal to what? A naught over k factorial, which is what I had in the last case, because everything from here is the same. That is to say, my y of x is going to be given by A naught by the sum from k equal to 0 up to infinity of x to the k over k factorial. In fact, this one is x to the 2. It's x to the 2 of 2k factorial, right, which is nothing but your A naught by sum from k equal to 0 up to infinity of x to the 2k over k factorial. And this, from elementary functions, we know that this is nothing but A naught by e to x squared. That's one example. And then the second example here that I have is says find the series solution for y double dash. So this will be example 2. Example 2 says find the series solution for y double dash plus y equal to 0 in the interval, of course, minus infinity less than x less than infinity. Right, again we assume the same solution, that is y of x is equal to A naught plus A1x plus A2x squared plus 1 and on, so that this is given by n equal to 0 to infinity of a n x to the n, and my y prime of x is nothing but a1 plus 2x plus 3a 3x squared plus 4x to the 3 plus on and on, so that this can be written as sum from n equal to 1 now up to infinity of n x to the n minus 1, and my y double prime is given by what? This term goes, and I'm left with the 2a2 plus 6, or in fact, let me not simplify that. Let me have this as 2 by 3, 2 times 3 by a3x plus 3 times 4 a4 plus on and on, and this is equal to what? The sum from n equal to 2 up to infinity of n times n minus 1 by a n x to the n minus 2. Right, so taking y and y double prime, then I sum those two, I get what? I get the sum from n equal to 2 up to infinity of n minus 1 an x to n minus 2 plus the sum from n equal to 0 to infinity of an x to the n, to equate that to 0. Right, I need to shift my index here so that the generic term is x to the n, and to do that I think this is now obvious. This becomes n equal to 0 up to infinity. This pops up. In fact, these two, they'll go up by a 2. So this becomes n plus 2. Right. And this becomes n plus 1. Right. By a n plus 2. And then this becomes times x to the n plus the sum from n equal to 0 up to infinity an x to the n equal to 0. And then I can rewrite this as the sum from n equal to 0 up to infinity of n plus 2 into n plus 1 by a n plus 2 plus a n, and take out x to the n equal to 0. Right. Now, since x is not equal to 0, this implies x to the n is not equal to 0. So this expression here can only be equal to 0 if this term inside the square bracket is equal to 0. So we have to solve n plus 2, solve this recurrence equation here. Right, solving for a2, so for an plus 2, this gives me minus an divided by n plus 2, n plus 1. Right, I need to transfer this to this side. Right, we have that an plus 2 is equal to minus an over n plus 1 by n plus 2. Right, so when n is equal to 0, when n is 0, I get a1, sorry, I get a2, which is equal to what? Minus a0 over 1 times 2. When n is equal to 1, I get a3, which is equal to what? Minus a1 over 2 times 3. Right. Without any loss of generality, I can multiply by 1. You know, this is 1 by 2 by 3. It doesn't change anything. Right. Because I can rewrite this now as a0 over 2 factorial. Then write this one as minus a1 over 3 factorial. Right. And then when n equals 2, when n is equal to 2, I get a4, which is given by what? Minus a2 over what? When n is equal to 2, 3 by 4. This is equal to what? a2 is given by that term there, so that I can rewrite this now as positive a0 over 2 factorial times, in fact this becomes 1 times 2 times 3 times 4, so that this is now equal to what? a0 over 4 factorial, and when n is equal to 3, I get a5, which is equal to minus a3 over 4 by 3, which is equal to positive a1 over 1 times 2 times 3 times 4. Right. This one is what? N plus 2. This is supposed to be 3, 4. Supposed to be times 5. So that this is times 5. Right. Minus, in fact, it's now positive. And this is nothing but a1 over 5 factorial. And I think the pattern is now clear. Right. So, we substitute. In fact, I have these terms here. I have a, okay, I can rewrite my y of x being equal to a naught minus, it was a1, okay, a naught plus a1 x plus a2, but a2 is nothing but minus a naught over 2 factorial x squared minus a1 x to the 3 over 3 factorial plus, so this is a naught 1 2 3 then 4, a4 is a naught x to the 4 over 4 factorial plus